Welcome to the first lecture of Unit 6 for Earth Science 1000. Unit 6 is going to be covering the Earth's dynamic atmosphere, the third in the series of four quote-unquote spheres in the Earth system that we've been looking at through this entire course. The atmosphere is the zone or layer of gas that surrounds the planet Earth. It interfaces with the Earth system both in the biosphere as well as the geosphere and the hydrosphere. The main interface we see is at the surface of the Earth, the surface of the geosphere and the surface of the hydrosphere, where either biological forces or physical forces or chemical forces, for that matter, can incorporate some of those gases from the atmosphere and can also release gases into the atmosphere. There's an exchange between the spheres at this interface. The Earth's atmosphere has several components. We're going to be looking at in this chapter specifically the composition, structure, and temperature of the atmosphere. However, in later chapters in this unit, we're going to be looking at moisture, clouds, and precipitation in Chapter 17, air pressure and wind in Chapter 18, weather patterns and severe storms in Chapter 19, and the final chapter in this unit is going to be world climates and global climate change. There's a lot of material in this unit, and we're going to try to move fairly quickly through it. So weather and climate. Weather and climate are oftentimes in our culture and society used interchangeably. However, they're vastly different terms. Weather refers to climate parameters that act on short timescales, short periods of time. Weather is constantly changing. A rainstorm in the afternoon is weather. A heat wave is weather. A cloudy day is weather. Climate, on the other hand, is a generalized composite of weather. That is, it's kind of an average weather or average pattern of weather-related parameters that exist over space and time. Climate can be viewed over timescales that are geologic, that is hundreds of thousands to millions of years, and climate can also be contextualized or viewed from a perspective of years to decades. However, it's very, very important to note that weather events are very, very specific in time and space, and climate patterns are very broad and general over time and space. It's difficult, not to say impossible, but it's very difficult to prescribe specific weather events, say very intense pattern of tornadoes in the Midwest or a particular bad hurricane year. It's very, very difficult to attach specific weather events to longer-term changes in climate patterns. However, there is some really relevant and recent research that seeks to do this. I caution all students from using those terms interchangeably. It's very important to know the difference and understand the difference between weather and climate. It would be akin or analogous to in say a healthcare perspective, where one patient in a hospital, their particular illnesses or conditions, you wouldn't necessarily be able to relate that to the broader population in a hospital. Say if one person in the emergency room has some coughing and some pneumonia, things like that, you wouldn't necessarily use that specific person to make generalized statements about the whole entire population of the hospital. You wouldn't say everybody has respiratory distress in the hospital. There's lots of different problems going on, or lots of different illnesses and conditions being treated in a hospital at any given time. Heart disease, neurological impairment, respiratory issues, other things like that. But if let's say you had 20 people in a hospital emergency room that all had similar symptoms, you might be able to make generalizations about a particular disease incident that was occurring in that particular space and time related to a broader pattern, say tuberculosis, an epidemic of tuberculosis or something like that. Hopefully that analogy can help those who are having a hard time understanding the difference between weather and climate. Hopefully that can flesh that out. Common measurements of weather are temperature, humidity, cloudiness, precipitation, air pressure, wind speed, and wind direction. Those are the things you see often on the nightly news report if you watch the weather. And those are measurements that can be climatological in nature. You can look at those parameters over broad periods of space and time as well. Now, the atmosphere is a gas layer surrounding the Earth. Air is a mixture of discrete gases. What that means is very specific gases. It's a mixture of different components. The main components of air are nitrogen, which is roughly 78%, and oxygen, which is roughly 21%. We humans mostly care about the oxygen. That's true, but nitrogen is actually very important for as a nutrient for photosynthesis. It's fundamentally required for life. Nitrogen and phosphorus are both required for life, or at least primary productivity, that is plant life, photosynthesis. Argon comprises about 1%. It's the next most abundant gas in the atmosphere. And from there on down, you have what are called trace gases. Carbon dioxide is the largest trace gas. That is, it's 0.04%. Or another way of writing that would be 400 parts per million. That is, there's 400 molecules of carbon dioxide in a million molecules of air. That's the same as 0.04%. That is 0.04 molecules of carbon dioxide in 100 molecules of air. That doesn't make a lot of intuitive sense, because how can you have 0.04 molecules of carbon dioxide? You either have a molecule or not. And so when you extend that percentage out, what it really means is there's 400 molecules of carbon dioxide per million molecules of air. Your textbook says it at 0.36%. 0.036%, but actually that's a dated number. Carbon dioxide in the atmosphere is actually steadily increasing, and has been for quite some time, since the Industrial Revolution in the 1800s and the 19th century. And it just recently, this past year, actually surpassed 400 parts per million. That's actually kind of an important number, and we'll get to that later on in Chapter 20. Other notable thing about carbon dioxide is it's called a greenhouse gas. That is, greenhouse gases are these gases that have this ability to absorb thermal radiation or infrared radiation. When solar energy travels from the sun through space toward the Earth, it comes in as light. When things absorb that light energy, oftentimes a proportion of that light is reflected back out or re-emitted back out, but instead of being emitted as visible light or ultraviolet light, those wavelengths, it's emitted as infrared radiation, and carbon dioxide has this ability to absorb molecularly those infrared wavelengths. That basically causes CO2 to act as a blanket around the Earth. Energy comes in, but the equal amount of energy does not escape. Again, that'll be very important later on in the course. Less abundant trace gases relative to carbon dioxide are neon, helium, methane, krypton, and hydrogen. There are some variable components of air. Now, as I mentioned earlier in the last slide, CO2 is changing, as are some other gases, like methane. But what are highly variable are gases related to water. Well, not related to water, actually water vapor, that is the gaseous form of the molecule H2O, or water. Up to about 4% of the air, air's volume is composed of water, but that depends on where you are on the globe, whether you're in a highly arid environment, an area with lots of evapotranspiration or very little evapotranspiration. If you think back to the graphic on the water cycle, or the hydrologic cycle, if you remember that water moves through the different spheres at different rates depending on where they are. And also you have what are called aerosols, which are tiny solid and liquid particles that exist in the atmosphere. Aerosols can be quite important, as water vapor and other vapors can condense on these solids. They also reflect sunlight, which can change the amount of solar radiation reaching the Earth, and which isn't scientifically important, but is certainly culturally important. The aerosols can add color to the sunrise and sunset. Ozone is another variable component of air, and that is usually in the upper atmosphere when oxygen joins together as 3 molecules of oxygen instead of the standardized 2 that we're used to breathing. Ozone is a molecule comprised of 3 oxygens, so it's O3. Ozone has a really interesting ability to block ultraviolet radiation coming in from the Earth. Ultraviolet radiation is very, very damaging to cells. That's why when you buy a pair of sunglasses, you look for a label that says UVA and UVB protection, or 100% UVA and UVB. Ultraviolet radiation can cause cell death. It's very important to protect your eyes from ultraviolet radiation. That's why you have those sunglasses, and that's what's great about the ozone layer in the upper atmosphere. Ultraviolet radiation can also cause skin cancers, again, which is why we use, or oftentimes recommended, to use sunscreen on particularly sunny days or times when you're going to be exposed to a lot of sun, either by intensity or duration. The ozone layer in the surface of the Earth has been compromised in the past. It varies. It's not uniform, particularly over the poles. There are layers of or sections of the ozone layer that are very depleted in ozone, and that actually can have a dramatic impact on the biology, especially for smaller organisms, single-celled, multicellular small organisms that only have a few cells. You get a little ultraviolet radiation down there, and that can really impact growth of plant matter, primary productivity, which if it causes too much decline in primary productivity, that can really impact food chains, especially in nutrient-rich zones of the world's ocean. Now, we just looked at the composition of the atmosphere. Let's look at how the composition of the atmosphere changes in a vertical sense with respect to the number of molecules that are in air as we go up. Put another way, what is the density of those molecules in the air in the vertical dimension, both from the surface of the Earth on up to the edge of the atmosphere? Scientists refer to that, and we all have heard this term before, as air pressure. Pressure can be thought of as the weight of air above a certain point, any point on the Earth. Now, what it really is the mass of the molecules in that column of air right above that point. So it really is a weight. Average sea level pressure is defined as, or was measured at, but is basically defined as about 1,000 millibars, which is about 14.7 pounds per square inch. So there are 14.7 pounds of gases per square inch when you're at sea level. Now, the scale that we use, millibars and psi and bars and pascals, are all interchangeably. They're from different systems of measurement. Air pressure decreases with altitude. That is, you go higher in a column of air. In this illustration, there are fewer molecules above you, and therefore the weight or the mass of those molecules is less. So pressure, that is the density of those molecules in a vertical dimension, really decreases rapidly as you go up. At about 3.5 miles vertical, you get to the point where you're above about half of the molecules in the atmosphere. 90% of the atmosphere is below 10 miles. And you can see this plot over here that shows pressure, that is, at sea level it's about 1,000. And as you go vertically in miles on this scale or kilometers on this side, you can see that pressure goes down. So at about 2 miles up, we're at about 700 millibars, about 30% of the pressure at sea level. If you keep going up to about, 5.5 miles, Mount Everest, top of Mount Everest, you're at about 300, a little bit more than 300 millibars. Remember, that is, you're about 30% of the density of air as you are at sea level. And remember, air is 20% oxygen, which is what we breathe. If you're at 30% of that amount of oxygen, the atmosphere, you're a climber at the top of Mount Everest is only able to, with every breath, they're getting about 1/3 the oxygen they would normally get in each breath down at sea level. And as you get upwards into the 12 to 13 miles or the 20 kilometer zone, you're very, very low pressure. You're at 100 millibars, give or take, or 10% of the density or pressure at sea level. So your 20% oxygen is, with every breath, you're only getting about 2% of the oxygen, or 1/20th what you would get at sea level. Now, the pressure structure of the atmosphere is one thing, but there's also a thermal structure of the atmosphere. And the atmosphere is divided, in scientific terms, based on temperature. There are 4 main zones of the atmosphere: the troposphere, going upward, troposphere, stratosphere, mesosphere, and thermosphere. The troposphere is the bottom layer. It's where temperature decreases with altitude. And it decreases at a rate that's called the environmental lapse rate, which is 6.5 degrees per kilometer in height and 3.5 degrees Fahrenheit per 1,000 feet. Those are equivalent rates. They're just in different terms, but either metric or British units. The thickness of the troposphere varies, and that's because there are zones that are higher up where temperature is still decreasing. That's basically caused by atmospheric circulation patterns. And the outer boundary, or the upper boundary of the troposphere, is called the tropopause. And that's where we switch into what's called the stratosphere, which is where temperature increases, moving up. It goes from about 12 kilometers to about 50 kilometers. You can see in this plot over here the layer of maximum ozone at about 25 kilometers in altitude. And the outer boundary of that, or the upper boundary of the stratosphere, is called the stratopause. Next up, we have the mesosphere, which is again where temperature starts to decline with altitude. It's the zone where we're kind of transitioning into outer space. It's where you see meteors that are space objects that are entering the atmosphere, where they encounter enough frictional resistance that they tend to burn up. That's why this graphic up here shows the meteor. The mesosphere goes from 50 to 80 kilometers, and we get to the mesopause, which transitions into the thermosphere, which has no well-defined upper limit. That is, it's kind of translates or transitions into outer space gradually. It has a fraction of the atmosphere's mass, and gases are moving at really, really high speeds. And if you know the aurora borealis or aurora australis, those spooky nighttime light shows that occur in the northern and southern high latitudes, that's where those things occur, where there's lots of ionization or ionizing radiation from the solar winds interacting with gases that are in the upper thermosphere. Now, Earth-Sun relations sounds like a little bit of meteor or astronomy, but it does have actual very, very important impacts into atmospheric circulation. So you might expect this section to fall in the next unit. However, we need to address the way the sun interacts with the Earth in order to understand what is happening in the atmosphere. Now, we know the Earth rotates on its axis and it revolves around the sun. We know that seasons are a result of changing sun angle and the changing length of daylight, and they're caused by which is caused by the Earth's changing orientation to the sun. So the Earth's axis is inclined by about 23.5 degrees. Remember looking at the Milankovitch orbital variations, where you saw precession, obliquity, and eccentricity change over long periods of geologic time. But the obliquity and the precession both relate to the changes or the angle that the Earth is inclined relative to the sun. And the axis is always pointed in the same direction over annual to decadal timescales. We know that precession changes the angle of that axis over long periods of time, hundreds of thousands of years. Special days in the northern hemisphere, which they're also equally special, I guess, in the southern hemisphere, but they're opposite, are the summer solstice, where the sun's vertical rays are located at the Tropic of Cancer. The winter solstice, which is where the sun is directly over the Tropic of Capricorn, and then the autumnal and vernal equinoxes. Autumnal equinox in the northern hemisphere, fall or autumn, and the vernal equinox in the northern hemisphere, spring, are where the sun's vertical rays are located at the equator. This graphic shows it a little bit better. You can see this line here is the Tropic of Capricorn, I believe. Yeah, Tropic of Capricorn. And this 30 degrees north latitude, the Tropic of Cancer, and we know that 0 degrees latitude is the equator. As the Earth rotates around the sun, the vertical rays are impacting these areas on the Earth differently. So this is a case where the sun's rays are vertically coming into this point right on the Tropic of Capricorn. That would be the winter solstice. This graphic right here shows it incorrectly. This point right here, which actually no, this point right here is right there. That would be point A. Point B would be somewhere, if it's 45 degrees, would be probably around the Capricorn or the Tropic of Cancer. And this graphic here, point C, is further up, where the angle of sun incidence is very, very, very low in the northern hemisphere. This graphic shows it a little bit better, and this shows how the Earth rotates around the sun. Its axis, as we learned in that a couple slides ago, is always at the same angle, roughly 23.5 degrees relative to the sun. And at this point in time, where the sun is vertically right above the right above the equator. That is the spring or vernal equinox. It happens in middle to late March, always around March 21st, 22nd, sometimes late in the night, 20th. As the sun continues to rotate in the annual orbit around the sun, at some point with this tilt here, the sun shows up as coming vertically right down here on the Tropic of Cancer, which is 23.5 degrees north latitude, and that is called the summer solstice. It continues around in its annual orbit. You have to imagine you're on the backside of this moon, and what it is, it's right on top of the equator again. So it's the autumnal equinox, September 22nd, 23rd, give or take a few hours. The sun is vertical at the equator, and as it rotates around in its annual cycle, all of a sudden in the wintertime, you've got your sun angle or your solar radiation incident intersecting the Earth's surface at the Tropic of Capricorn, 23.5 degrees south. That's the winter solstice. This shows characteristics of solstices and equinoxes. Again, we're talking about how the sun, where the sun is oriented, or how the sun's energy is intersecting the Earth at different times of year. And you can see the most vertical incident, or the most vertical section of exposure to the sun is around that northern hemisphere Tropic of Cancer at 23.5 degrees. You don't have the most sunlight at that point in time, but you certainly have the most radiation, or the most direct radiation. In the December solstice or the winter solstice, solar energy is concentrated in the southern hemisphere. That is this section of the sun below the equator. And at the equinoxes, the equinoxes, the spring and autumnal equinox, the sun's energy is concentrated most directly on the equators, and equally distributed on the upper and lower hemisphere, or the southern and northern hemisphere. Now, atmospheric heating occurs due to solar energy incidenting or intersecting the Earth's surface and the Earth's atmosphere. Atmospheric heating, heat is always transferred from warmer to cooler objects. That is, you can think of cool objects as lacking heat, and warm objects as having heat energy, and that energy always tries to balance out. So it's heat energy is not a negative or positive thing. It's only it's basically a positive thing. It's only there. The absence of heat, when something is cool, only means that it has an absence of heat energy. And so heat energy, like lots of things, tends to want to equilibrate, tends to want to balance out. And so when something is warm, comes in contact with something that is cool, some of the energy from the warm object or warm thing will move over into the cool thing until that cool and warm thing are equally balanced in terms of their energy, in this case, their temperature. So there's two mechanisms of heat transfer. One is conduction, and that is molecules interacting physically with one another and passing their heat on through a system. And the other is convection, which is mass movement within a substance, usually vertical. You learned about this in the plate tectonic zone, the plate tectonic unit, where warmer things tend to rise because they're less dense. Their molecules are vibrating, have more kinetic energy, or vibrating faster, tends to rise and displace cooler areas, which will then fall with density based on density differences, and come into contact with whatever is heating that material. The third way of absorbing heat energy or transmitting heat energy is through radiation. That's electromagnetic radiation is the strict or precise term. Now, radiation moves at the speed of light. Light is radiation, or what we think of as light, which is really visible light, which is a small section of the radio or electromagnetic radiation spectrum. The speed of light is 300,000 kilometers per second in a vacuum, or 186,000 miles per second in a vacuum. That's very, very fast. And in a vacuum, it means in a space where there is no other interfering molecules. Outer space is the closest thing we have in our universe to a vacuum. Electromagnetic radiation consists of different wavelengths, all with different properties. However, it's fundamentally a transfer of energy, or fundamentally comprised of energy. It's just energy with different characteristics. So gamma rays, starting at the low end of the electromagnetic spectrum right here, have very, very short wavelengths. And you move all the way up through X-rays, ultraviolet radiation. Remember, the ozone layer protects us from this ultraviolet radiation, which can interact with our cells, with biological cells, and cause lots of cell damage and death. Visible light, you'll notice, is quite a small little zone of wavelength. And within that visible wavelength spectrum, you can see that there's different wavelengths within that spectrum, starting with the shortest, which is violet, moving on through the spectrum to red. And it's the colors of the rainbow. And in fact, the rainbows have this same pattern, and that's due to the fact that that light and visible light and lights of specific colors have this relationship of wavelengths. Moving on up, we've got infrared, microwave, television waves, which aren't naturally occurring waves. We produce them, human beings who generate TV signals. Shortwave radio waves, all the way up to long radio waves. Electromagnetic radiation is governed by natural laws, by basic laws. All objects at whatever temperature, unless they're at absolute zero, emit radiation. It's called black body radiation. Hotter objects radiate more total energy per unit area than cooler objects. So things that are warmer, that have more heat energy, will radiate more radiation. And the hotter the radiating body, the shorter the wavelength of maximum radiation. And objects that are good absorbers of radiation are also typically good emitters as well. So it has to do, it's a similar concept to water heat capacity. Water has this incredible ability, or liquid water has this incredible ability to absorb energy as well as emit energy. This graphic shows how solar radiation is transferred onto the Earth's surface and how it is absorbed essentially by the Earth. That the atmosphere is largely transparent to incoming solar radiation. It's largely transparent to incoming solar radiation in the visible spectrum. Remember, we talked about how ozone absorbs a lot of the UV spectrum that comes through. Solar radiation, it shines down or intersects with the Earth's surface, transmits through the atmosphere relatively in a transparent manner. Atmospheric effects that do occur, you can get reflection. Another word for that in geologic or Earth system terms is called albedo. That is the amount of reflected energy that reflects back out into space due to, number one, aerosols, clouds, water droplets, etc. There's the atmosphere has another effect called scattering, which causes solar radiation to refract and change its pathway. And there's also absorption. There are components in the atmosphere, particularly water, methane, and clouds, that can absorb some of that solar radiation. Water especially, because remember, water has a tremendous heat capacity. Now, most visible radiation reaches the surface. Again, visible radiation, not ultraviolet, not infrared. And about 50% of that radiation is absorbed at the Earth's surface. And remember, what we saw in the last slide, that material or matter that is generally a good absorber of radiation is also usually a good emitter of radiation. So some of that radiation that is absorbed by the Earth's surface is emitted back out, is purged from the Earth, and that we can see this graphic of what the greenhouse effect is. Now, solar radiation that transmits through the atmosphere and is absorbed by the Earth, about 50% of incoming solar radiation is absorbed by the Earth. The Earth re-radiates that radiation at longer wavelengths. So if we look back at the electromagnetic spectrum, if it's visible light coming in, it's going to re-radiate it at either infrared or potentially microwave or radio wave wavelengths. So it re-radiates at longer wavelengths. Fortunately or unfortunately, depending on the period of deep geologic time you're in, whether you're at 540 million years ago when the Earth was covered in ice during a period called the snowball Earth, in which case this situation would be very good, or now where the Earth is not covered in ice and things seem to be getting warmer in an uncontrollable fashion. Longer wavelength radiation that is released from the Earth is absorbed by the molecules that exist in the atmosphere, or many molecules that exist in the atmosphere, namely carbon dioxide, water vapor, and methane. Heating of the atmosphere based on this reabsorption of emitted thermal infrared radiation from the Earth's surface is called the greenhouse effect. Now, temperature variations on the surface of the Earth vary widely. You can imagine, and most people know intuitively, where the warmest zones on the surface of the Earth are. If you think about it, most of those zones are near the equator. And the coolest zones are typically near the poles. That's why the poles are covered in ice typically, and the equators don't have very much ice at all. In fact, they're quite warm. So temperature variations on the Earth's surface, the most important factor controlling those is the amount of solar radiation that is incoming, or the receipt of solar radiation. Other important controls for the temperature variations of the atmosphere and the Earth are differential heating of land and water. That is, land heats more rapidly than water. Remember, water soaks up heat and doesn't change temperature until it soaks up a lot. Land gets hotter than water, because water has this latent heat of evaporation that takes a lot of energy for water to go from liquid to gas. Land cools faster than water, and land gets cooler than water in general. So coastal zones that are near water tend to be more moderate in temperature than inland zones. As you can see by this plot down here on the right-hand side, Vancouver, which is a marine environment, has generally higher minimum temperatures in the winter months and generally lower maximum temperatures in the summer months, whereas a continental environment, which gets cooler faster and gets warmer faster, tends to have much lower minimum temperatures and much higher maximum temperatures. You can see the same example on this plot down here on the left-hand side, where leeward sides, where the wind is traveling over land, versus windward side, where the wind is, general weather patterns are traveling from the sea toward land. In California, you have a much more moderate climate, where the minimum temperatures are generally higher than they are on the landward, where solar radiation has more time to interact with land, and the maximum temperatures are generally lower than they would be otherwise. The other controls of temperature are, of course, altitude. The higher you go, we saw that in the thermal structure of the atmosphere and the environmental lapse rate. Other important controls: altitude, geographic position, cloud cover, which absorbs incoming solar radiation, and albedo. Remember, albedo is the reflection of solar radiation back out to space. Global temperature patterns generally follow your intuition. That is, they generally follow what you would suspect them to follow. That is, areas of maximum solar radiation tend to be warmer, and areas of minimum solar radiation tend to be cooler. Remember, the patterns of solar radiation, over the surface of the Earth related to the orbital variations, or orbital patterns of the sun, orbital patterns of the Earth relative to the sun. Temperature tends to decrease poleward as you go from the tropics, that is, going toward higher latitude from the equator, either north or going to higher latitude south. Temperatures tend to decrease. Isotherms are lines which show zones of equal temperature. So everywhere along this line, for instance, this 20-degree line, it's not 20-degree latitude, this is 20 degrees C. It's called an isotherm, that is a zone of temperature equality. Isotherms exhibit a latitudinal shift with the seasons. That is, in January, when the solar energy is concentrated around between the Tropic of Capricorn, about from here to the equator, you can see this zone is a lot warmer in the southern hemisphere. Now, as if we move to our spring, where the sun is transiting and concentrated solar energy is concentrated in the northern hemisphere between the Tropic of Cancer and the equator, temperatures are higher in the northern hemisphere. In the southern hemisphere, isotherms tend to be straighter. You can see that on these two plots. and isotherms tend to be more stable. That actually has to do with the absence of continental mass in the southern hemisphere. Remember, the southern hemisphere is considered the water hemisphere, and the northern hemisphere the continental hemisphere, if you think back to those patterns of continental arrangement. So that's about it for chapter 16. We'll move on to chapter 17 next. And thanks for taking the time to listen.